Hi everyone, and welcome to the demonstration of the Semantic Adhesive Selector. The Semantic Adhesive Selector is an interactive system that supports adhesive experts in finding appropriate adhesives for a specific use case they have by utilizing semantic web technologies and symbolic reasoning. In this video, we will go through the process of generating the knowledge graph that the Semantic Adhesive Selector utilizes to generate recommendations, and then we will show how the user interacts with the Semantic Adhesive Selector to input their use case requirements and get some adhesive candidates. While working with adhesive manufacturers and suppliers, we observed that they often don't rely on structured, organized data, but rather on loosely structured knowledge bases, such as the ones that we see here, with a few definitions and a few apparent connections between different properties. However, schemaless data like this are difficult to apply reasoning to and draw observations from. The first primary task of the Semantic Adhesive Selector is to generate a structured knowledge base for the data in hand in order to enable semantic interoperability and reasoning. For that reason, we sit together with adhesive experts to encode, understand, and fix existing data and build automated pipelines to transform our initial data into an interoperable knowledge graph. This knowledge graph is then utilized by our IDPZ3 reasoner to provide recommendations to adhesive experts. We use knowledge gathered by adhesive experts and our developed glue ontology to pre-process the original adhesives data and build declarative ETL pipelines for their transformation to knowledge graph. In this process, we utilize prominent semantic web technologies such as YAML and RML mappings, as well as RDF knowledge graph construction tools like MorphKGC within our ETL pipelines. The final product is an automated pipeline that adhesive experts can activate whenever they have updated their internal data to also push a new version of the adhesives knowledge graph in our GraphDB instance. This is done by running a single command. For example, when we have updated the original adhesives data that we have, we can run the knowledge base builder to rebuild our knowledge graph using the mappings that we have developed in collaboration with the experts. The mappings built on top of our ontology are applied to the updated data, and the new knowledge graph version is constructed from our adhesives data lake. When the knowledge graph is ready, we push it to GraphDB, uploading a new version of our adhesives graph. After the update process has been completed, the new graph is ready to be queried to extract recommendations from. Here we can see an example of a graph adhesive visualization in GraphDB. For example, we can see here the RL dyed 2011 adhesive and all the recorded attributes that have been added into our graph. And we can see that it belongs to the 2C epoxy adhesive family, and if we extend this family, we can also find other adhesives of this family that are included into our graph. Our generated knowledge graph is connected with our interactive adhesive selector interface to enable the inference of recommendation of adhesives based on use case requirements that experts set. In this interface, the underlying knowledge base is represented by symbol tiles, and so each symbol in the knowledge base corresponds to a symbol tile in the interface, such as the symbol tile for adhesives, which contains 54 possible adhesives that are currently loaded in our knowledge base. The idea is that by entering constraints or values over the adhesive, this list of adhesive goes down step by step up until the point where an expert is satisfied and has a short list of adhesives to start testing with. Experts can filter out adhesives by entering their requirements, which you can see here with symbols such as the bond strength, the flexibility that it should have, the temperature resistance or the temperatures it can withstand, and the materials to be glued together. Or in the production part, we can set the minimum application or the maximum application temperature and other requirements. Okay, so let's use an example. Let's say that I want to glue a composite to a steel. Then I could enter these values as follows. And what we see is that the system immediately starts deriving new information. So in that case, if I enter this, it starts deriving information on these substrates themselves. So for instance, a composite is not transparent to UV, it's not porous, etc. If we scroll all the way up, we can also see that the list of adhesives has gone down. It has reduced from 54 to 50 possible adhesives. In other words, 4 of these adhesives were not suitable because they didn't bond well to either steel or composites. Okay, let's enter more requirements. Let's assume that we want to have a bond strength of 12 megapascals, so the bond is strong. Then, if we go in at the top, we can see that the list of adhesives has shrunk even more, going all the way down to 18 possible adhesives. Let's keep going for a bit. I know that we want a very flexible adhesive and also have a low environmental impact. If we enter these constraints, we find that there are only 10 adhesives that satisfy these constraints, which belong to one of 5 adhesive families. And so this should allow a glue expert to start testing this shortlist in a lab. Of course, this was quite a simple case, and so there weren't too many values to be set, but it shows the general principle behind the tool. Every time we enter a value, it starts deriving new information. Moreover, our tool can explain why it was able to derive information. So for instance, the system has derived that our adhesive will be vibration dampening, and I can click on this to ask for an explanation why. And so in this case, it tells me that I required a very flexible adhesive, and there is simply a law in the system that says that an adhesive is vibration dampening if it is very flexible. In this way, if I don't want my adhesive to be vibration dampening, I immediately know what went wrong and what I should undo. For instance, we can undo the flexibility requirement if we don't want our adhesive to be vibration dampening. So this concludes our demonstration. First, we showed how we use semantic web technologies to build scalable automated pipelines for constructing interoperable graphs from our initially loosely structured data. Then we showed how our graph is plugged to our interactive adhesive selector interface to enable symbolic reasoning for adhesive experts, allowing them to come up with a final shortlist of adhesives to test given some use case requirements. Thank you for your attention.